So I think we can start. So everybody's here. I assume you're a little bit tired, but this is the last presentation, but not the least. So give a big round of applause to Mario. Today he is going to present Zero Trust Multi-Tenancy vCluster and Cilium across hybrid cloud. Nice. Cool. So once more, the stage is yours.
Thank you very much for the introduction. It was very nice. So first of all, thanks to everyone in the audience that came and took interest in this talk. And it's been really nice for the past 2 days because I've actually gotten the opportunity to talk and meet a lot of you. So it feels more like speaking to a group of friends and less to a foreign audience. And that's really, really nice. So today I'll be taking you through a journey of designing a multi-tenancy platform on Kubernetes that has the concept of zero trust at its core. A little bit about me. So my name is Mario. I work as a public cloud engineer at Vodafone Intelligent Solutions. And I'm a big Kubernetes and CNCF fan, as I'm sure many of you here are. And our journey today is going to have a few stops. So I will introduce the concept of zero trust in the context of Kubernetes and see how running multiple tenants on the same host infrastructure challenges that definition. I will introduce 2 open source projects that help bridge this gap. And then we're going to see together what happens when you leave the safety of your network and respectively that of your cluster. Essentially, zero trust can be boiled down to 3 main pillars. Explicitly verifying your identities, making sure that if you have a compromise in a workload, that compromise doesn't spread to the rest of your infrastructure, and giving our identities the least amount of permissions possible that they need to prevent undesirable actions. Now, these 3 pillars are reunited under the same umbrella of continuous monitoring. So zero trust is not a one-time thing, but rather a continuous process. Now, specifically in the context of Kubernetes, we can map zero trust to 6 fundamental concepts. Well, we have to protect our host that our workloads run on. We have to define who can talk to who. We have to make sure that everyone gets a fair slice of resources. We have to logically separate our concerns. We need to define who can do what. And we also need to continuously audit and report on the above. So one thing is for certain, zero trust requires a holistic approach. Now, Kubernetes already provides an arsenal of tools to address these challenges. But the vanilla ones, unfortunately, fall short when confronted with multi-tenancy. So for example, we have runtime classes, which are tough to enforce on all of the workloads of a particular tenant. And pod security standards are useless on a mislabeled namespace. Network policies are not nearly as granular as they should be, so they completely miss layer 7 traffic from their scope. They rely on ephemeral properties more often than not, instead of immutable identities, and they cannot enforce traffic leaving your cluster boundaries. It is difficult to set a global resource cap on a tenant, particularly when they choose to spread their workloads across multiple namespaces on the host. Role-based access control can quickly become tedious. And auditing is great for seeing who calls your API, but they don't give you visibility into your network traffic. And not to mention that many of these restrictions also damage the flexibility of your developers. So this is precisely where I want to introduce the first open source project that we're going to talk about today, or the open source part of that project, and that's vCluster. And I want to see a show of hands in the audience who here has used or heard about vCluster before. OK, so we see a couple of hands. So maybe for you, the information that I'm about to share is not going to be new, but it's still useful. vCluster essentially is a lightweight Kubernetes distribution under the hood. More often than not, it uses K3s. And its main purpose is to allow us to run Kubernetes inside Kubernetes. vCluster can run on almost any platform, and even recently they made it also run on Docker as a container. It's called vCluster in Docker, or Vine for short. So chances are, if you can run a container, you may also be able to run vCluster. Now, in itself, it is essentially a bundle of components. We have an API server and a controller manager that we get from our Kubernetes distribution. We have a syncer, which is their proprietary component. And optionally, if you want some sort of state persistence, we can run etcd with it. Now, we have to bear in mind that vCluster, at its core, is just data plane isolation. So your workloads still get translated to your host cluster. And there they get treated as normal pods by your host cluster components, such as your scheduler or Carpenter when it tries to provision your nodes cluster, autoscaler, and so on. And since vCluster incorporates its own API, you can deploy workloads inside vCluster as you would to a normal cluster, either through kubectl or through your favorite GitOps tool. But vCluster is not only limited to the scope of workloads. For example, you can synchronize storage classes, use them to build persistent volume claims, sync them back so your CSI driver picks them up. Same goes with ingress classes, which you can use to build ingress objects for your application. And then you can sync those back so they get picked up by your ingress controller. Or generic CRDs, which you can use to build custom objects. As for how we can leverage vCluster to provision a tenant space, so here our approach consists of a centralized platform repository that basically takes an array of tenant specifications and feeds those tenant specs into an Argo CD application set. And this app set provisions two things. First, the actual tenant space, which is vCluster and the namespace it runs in, as well as an Argo CD project that helps scope down that specific tenant's permissions if you have to reuse the same Argo CD across all of your tenants. The second phase is vCluster can expose its connectivity parameters through a kubeconfig type secret, and then you can pick your kubeconfig secret up with, let's say, external secrets operator and translate them to a format that is understood by Argo CD as a cluster format secret. And once you have that, which allows you to deploy the vCluster, your tenant can log in with their user. They can integrate their private GitHub repository and deploy their workloads inside vCluster. So let's see that in practice. So here we define a new tenant, chosen the name to be tenant1, and the namespace the same. Right off the bat, we can pin down the vCluster version and also pass a list of those whitelisted repositories that our tenant can deploy from. We have a list of best practice values, but we can pass overrides to them. For example, when we want to synchronize those pods, we want to enforce a particular runtime class on. Here I've chosen runC, which is really basic, but you can choose something like gvisor if your infrastructure supports it. And you can define certain policies. So here we have a resource quota, custom resource quota that's going to apply globally to our tenant. And I choose to deploy the bundle of best practice network policies that come with vCluster. As for pod security standards, I can label the namespace where all of those tenant workloads are going to run right off the bat. And I can do something like an audit action on a baseline level, just for the purpose of this demo. As for tenant authentication, here I've chosen something locally, but you can integrate it with your favorite IDP. And for that secret that repo that we've whitelisted earlier, we can pass an AWS Secrets Manager key to pull those repo secrets from there and instantiate them locally. We commit and we push our changes. And then after a couple of seconds, we can see that we get two applications in Argo CD. One is tenant 1, which is the actual vCluster and the namespace it runs in. And the other one is tenant 1 Bootstrap, which has everything else. So the secret synchronization that I've talked about earlier, role-based access control, the Argo CD project, and so on. Now we can log in with that newly provisioned user. And we can choose to deploy a workload to the only project that we're allowed to deploy to, pulling from the only source that we've whitelisted, and choosing the only destination available, which is the vCluster itself. And it's exposed by its name and the namespace. So that would be tenant1.tenant1 in our case. And in a couple of seconds, sure enough, the workload's going to be there. So when we have a look, we see that we have 4 pods. It's core DNS, tenant 1, which is the actual vCluster, it's etcd, and our sample workload, which is in the default namespace. And if we have a look at that runtime class property from earlier, we can see that it is, in fact, run C, as we expect, as well as the network policies that were applied, which govern traffic to the vCluster control plane, DNS resolution, the snapshot controller, and in between the vCluster tenant workloads themselves. We can also catch a glimpse on the global limit range that was applied for that tenant, as well as the custom resource quota that we've defined. And the label on the namespace, which is, as expected, pod security audit baseline. Now, vCluster, if tuned correctly, can satisfy many of these requirements already. So you can enforce runtime classes for workloads at sync. You can enable pod security standards on the entire tenant by labeling the one namespace which you have in your host. You can enforce a global resource quota and a limit range. You end up with a single namespace on your host, which is easier to manage. And you can relax role-based access control, knowing that the scope of RBAC inside the vCluster will not affect other resources on your host infrastructure. And that's it. Or maybe not, because unfortunately, the network policies in this case, they're scoped to that vCluster box itself. So what happens when we go outside this box? What happens if we want to access our tenant resources from somewhere else in the cluster, right? So we need to secure this network traffic somehow, and you'd ideally do it with network policies. But how do we address some of the shortcomings we've outlined earlier? So this is precisely where choosing the right CNI can come to the rescue, and that's Cilium in this case. And Cilium is essentially a Swiss Army knife of container networking. So at its core, it is a container networking interface, a CNI for short, and it's special because it relies on the eBPF technology. Now, eBPF has several advantages, but the most important ones are the fact that you can get better performance, and you get enhanced observability into that network traffic at the kernel level compared to its other IP table counterparts. That's doubled by the sidecarless service mesh function of Cilium, which means that you get less resource overhead. And it also brings to the table functionality such as service discovery, mutual authentication, mutual TLS, and more granular networking decisions because it's capable to operate at that layer 7. We're going to see that in a second. And the beauty about Cilium is that it's able to take some of these features even beyond cluster boundaries, where it's able to establish a unified identity estate across all of your clusters that are interconnected. So in a typical Cilium deployment, that's mainly possible through the 5 key components that it entails. We have an agent running on each node, which provides that networking capability and also the network policy enforcement. We have the operator, which is the brains, so it does IP address management and certificate management at the cluster level. We've got Envoy, which often comes with Cilium, and it provides us that layer 7 functionality within network policies. Hubble, which is the way we can do that deep packet inspection within Cilium, and all that data is aggregated by Hubble Relay, which exposes both a UI and a CLI for you, the user, to be able to visualize that data. Now, I've mentioned identities briefly earlier, so it's worth defining what a Cilium identity is. It is a compound, unique per workload concept, and it's made of the different specifications that go into defining a workload. So that can be the namespace it runs in, the labels you apply to it, the service account it uses, and optionally, if you have a multi-cluster deployment, the identity of the cluster where that workload runs. And because of this, we get what I can call a upgraded network policy. So it is layer 7 aware. It can enforce HTTP rules, methods, and paths. DNS or hostname aware, and also it operates at that identity, with that identity principle, especially when we're talking about reserved identities, which is in concept in Cilium. That means the immutable identities, such as the cluster's API, the node that your workload runs on, other nodes, the world outside your cluster, and so on. So just a simple demonstration of how CNPs work. We've deployed a metric app to our vCluster. It's a very simple container that exposes one endpoint, which is /metrics. And we've got a scraper app that's basically just connects to that metrics app periodically, nothing else. And if we look at that Cilium network policy, as I've shown earlier, now we have an HTTP rule to only allow get on the metrics path from workloads that are labeled with app platform scraper, and that run in the platform observability namespace. And if we get the logs of that scraper, we can see that we get those container metrics. So the connection is successful, right? And this is also visible in Hubble UI. So you can see that the traffic is being forwarded, everything is green, nothing is limiting the communication between these two specific pods. But if we try to scrape a different endpoint, which is health, we get that layer 7 message, that's access denied. But also, if we try to do the same connectivity test from a pod that is not labeled, such as bad pod in our case, after a few seconds, we get a connection timed out error. And this is also visible in Hubble. So if we zoom into our metrics app, and we filter for dropped verdicts, we can see those two types of dropped connectivity flows. So we have from our scraper to our metrics on that health endpoint, which is dropped for an unknown drop reason. That's usually a layer 7 issue. And also the dropped connectivity from our bad pod to our metrics app, which is dropped for a policy denied reason. And we can also catch a glimpse into the complex identities that Cilium constructs for each of our workloads that are based on the labels, on the namespace, and on the service account that our workloads use. Now that's great for securing traffic in a cluster where you have all the nodes that are running in the same network and you have that sort of network level trust. But what happens if we leave this network? What happens if we choose to push our tenant to an external node in a different network that's peered to our original network? Now, in situations like this, you'd want to verify the authenticity of your workloads. And Cilium provides mutual authentication functionality, typically through the usage of Spire. And for who hasn't heard of Spire, Spire is a runtime environment of SPIFFE. That stands for the Secure Production Identity Framework for Everyone. And in a gross generalization, in our case, SPIFFE is basically a blockchain for our workloads on that cluster. And the integration with Cilium looks a bit like this. So we have a Spire server, which is the supreme identity authority in our cluster. It attests its agents that run on each node, and those agents basically are allowed to issue identities on behalf of Spire server. And then the Spire agents can issue something that is called SVIDs, or SPIFFE verifiable identity documents. Well, actually, these SVIDs are requested by Cilium on behalf of the workloads it manages, and they bind, so Cilium binds these SVIDs to the unique identities of its workloads. Once these SVIDs are in place, Cilium then negotiates a session, and then the connectivity can proceed. To activate it, it's quite simple, YAML speaking. So you tell Cilium you want it, you tell Cilium you want to use Spire for it, and then you tell Cilium optionally to install and manage Spire itself. But maybe mutual authentication is not enough. Maybe you also need some encryption between your nodes, considering that traffic leaves your cloud network. So that's possible in Cilium, because Cilium can establish VPN tunnels between your nodes, and it does that using the open source WireGuard protocol. And to activate that encryption, you just flip a switch, and then you select the protocol. So that's usually WireGuard or IPsec. And to have a look at this in practice, we've deployed a new tenant. So this is a tenant hybrid. And we can see it's healthy. So we've got the vCluster pod, and also it's etcd pod for state persistence. And we've deployed our metrics app from earlier to that specific hybrid tenant. Now we go to our cluster, and we have 3 nodes, 2 EC2, and 1 is an edge node external. And if we get the pods from our hybrid tenant, we can see that all of them have been forced to be scheduled on that specific edge node. We see the topology of Spire, so we have 1 Spire server and 3 agents, 1 of them on each node. And the Spire server provides quite a useful binary, I would say. So first of all, it allows you to check the health of the service, which is the first thing you want to do. It's healthy. And that same binary also has other functionality. So you can see the list of attested agents that I've mentioned earlier. Should be 3 because I have 3 nodes, but I have an attestation from a node that I deleted from my cluster. And also we can see the identities that are allowed to request SVIDs and consume SVIDs. So in this case, operator requests and Cilium agent consumes those identities. And we have a second Cilium network policy. So it's exactly the same as the first one with a small difference. We enforce the authentication mode on our ingress rule. So basically this means that if mutual authentication is not performed, then the connection won't be possible. We'll get the endpoint ID. This is a unique ID that Cilium assigns and manages for each of its workloads. And we'll use this to see how SVIDs are actually issued for our pods. So we'll pass that SPIFFE ID filter, and we can see that the parent ID is Cilium operator, which means that it's the Cilium operator who requested this SVID on behalf of the pod. And just to test the connectivity between our scraper and our metrics app is successful. So we get those container metrics. We'll grab the name of the Cilium pod running on the same node as our metrics app. And that's useful because you can actually get the logs of that pod, of that Cilium agent pod. And you can filter for successfully authenticated messages. And here you can see 2 essential pieces of information, right? You have a local identity and you have a remote identity. And maybe, as you may have guessed, that local or that remote identity will match the identity of our scraper, which is the one initiating this connection between the 2 pods. And the local identity will match the identity of our metrics app, which is the one receiving the connection, or in other words, the one that we've applied the policy on. Everything that we've shown in the console is also visible in the Hubble UI. We scope down to our metrics app. We see that now on that connectivity flow, we have a little log for whoever is more visual, and that denotes the enforcement of mutual authentication. And we see that in our flow logs, we see that the first packet is actually redirected to Spire for authentication. Now, what if we move outside the cluster? What if we schedule our tenant workloads to a completely different cluster entirely, right? How can we govern these identities that we've been talking about in a unified manner across our entire estate? So this is where we would leverage something like Cilium cluster mesh. Simply put, Cilium in each cluster runs a database, KV store or key value store, which is a database for all the identities of the workloads that Cilium manages in that cluster. The essential component here is the cluster mesh API server, and once these two authenticate to each other, a bidirectional sync between these identity databases can begin. And this is precisely the process that allows Cilium in cluster 1 to know about all of the identities in cluster 2 and vice versa. And this lays the foundation for many useful Cilium features, such as global services, where you can get Cilium to actually extend its service mesh functionality across cluster boundaries. Since Cilium is paired with other clusters and it knows about all of the identities in those other clusters, you can define network policies that take those identities into account or that take cluster identity into account. And to activate it, there are a few steps. So you have to deploy that cluster mesh API that I've mentioned. You've got to expose it outside the cluster through a load balancer service. And then because we are using Helm for this deployment, you have to tell Cilium from the get-go how to reach the other cluster. So in this case, the address, the FQDN, and the port. And for our last demo of the day, we've got a successful cluster mesh connection between two clusters. One is on EKS, the other one is bare metal. And what we'll do, first of all, is we'll grab the dominant label of one of our pods. So in this case, that would be we'll choose the metrics app that's running inside vCluster that we've been talking about. And we can see that that dominant label is app equals metrics app. And that's exactly how Cilium UI is going to represent this pod by that specific label value, to be specific. We've also exposed our metrics app through a service. So you can define those inside vCluster and synchronize them to the host as well. And what's special about this service in particular is the fact that we have a label on it. It's service cilium.io global true. And this is going to tell Cilium that you want that global service functionality for that specific service. We get our updated Cilium network policy, and because we're in a cluster mesh setup, now we can actually enforce a rule that is dependent on the ID of the cluster where our workload runs. I keep switching the colors for visibility, that's fine. And we'll switch to our EKS cluster. And in here, if we interrogate Cilium, we can see that Cilium in cluster 2 knows about the identity in cluster 1, judging by that dominant label. And we can also see that it takes into account the ID of the first cluster. This is a Hetzner cluster, to be more specific. And we've created a mock service. So this is a prerequisite for global services. You need to have the same service name on both clusters. But here, this is just a simple mock. We've set shared to false because we have no endpoints to contribute to that global service load balancing pool. The only purpose of this service on cluster 2 is so we can get our scraper to connect to our metrics app using that local service FQDN on the metrics endpoint, which is allowed as we'd expect. But if we switch back to our first cluster, and if we run the same test from a scraper that's in that cluster to the metrics app, we'll get a connection timeout after a couple of seconds. Because the Cilium network policy doesn't allow anything in the first cluster to connect to that workload in the first cluster. And now the beauty is that on Hubble UI, we can also see the cluster that our workloads run on. And if we scope down to our metrics app again and filter for dropped traffic, we can see that it's particularly that scraper that runs in the same cluster as our metrics app that cannot establish a connection. The verdict is dropped, and the reason is policy denied. And that's about it. So if you add Cilium on top of that vCluster layer, you complete this picture and you get granular layer 7 aware policies that are aware or that can work across cluster boundaries. And you also get in-depth traffic inspection via Hubble. So the main takeaways here would be the fact that namespaces are unfortunately not enough for multi-tenancy. Identity is stronger than location, so this means that instead of relying on ephemeral properties such as IPs, we choose to rely on immutable stable properties such as the identities that Cilium provides, and the fact that zero trust is composable. So you have to leverage multiple tools to satisfy all these requirements. And that's it from my side.